You seeing it? Away.
Yeah, no,
Okay.
yeah, we see the slides, yeah.
So I'm not going to repeat the joke with the phone, right? Okay, so what you see here, I already spoiled that. You see a singular. And on this picture, you see a plural, 3 glasses. Okay, and this is what this talk is going to be about. And on this slide, you should see nothing in a way. At least you don't see any glasses. And it's the question whether this is a singular or a plural. I would put it in the plural category. All right, so let's have a little look at language. In the English language, we have two different categories of number, and one is called the singular, and it's basically a property of nouns. And if I say my computer, the noun computer is in singular form. It's not only nouns that can come in singular and plural forms, also verbs can. For instance, if I say my computer and use it in a sentence, I need to use the singular form of the predicate. So my computer runs would be correct. My computer run would be wrong. Runs is also a singular and singular form, and it requires a singular subject. By contrast, in plural, my computers, as indicated by the plural s, is a plural form of the noun. And accordingly, I need to use the plural form of a verb with it. My computers run. So English is highly under constrained, but in this case it works because there's different, you can tell by the fact whether there is an S or not, whether it's a singular or plural form. Okay, so that's the takeaway from this slide, is that the distinction between singular and plural does not only apply to nouns, it also applies to verbs or predicates, or as we will see, functions. So let's have a look at the semantics of the syntactic forms of plurals and singulars in English, in the English language. The first thing is that plural applies only to so-called countables. What are countables? Well, countables are basically objects, things that can be identified. In a programming language, things that have identity or reference. So for instance, we can have one computer, we can have two computers, but we cannot have one snow or two snows. Snow cannot be identified. It's just a phenomenon or something. But what you can do with snow and other masses like liquids, you can contain them, and then you can give them numbers. You can have a shovel of snow, or you can maybe you can even have a glass of snow, and then you can have two, and that's the way to count them. Another thing is, if you have two singulars, you can construct a plural by using a conjunction. Like my computer and your computer run, and the noun phrase is clearly a plural as indicated by the plural form of the verb run. So that's a constructor of a plural. We can also deconstruct plurals into singulars. And for this, we use a construction like this one: of those computers, each runs, which may remind you of a for loop in a programming language. Computers is many, and then each is singular, is one. And as you can see by the number of the verb, runs is singular, so each must be a singular. And last but not least, we can reify plurals into singulars, like a cluster, for instance, which may refer to my computer and your computer if they are a cluster. So reification is very important. We see that many times over in this talk. Okay, so let's have a look at the occurrences of plurals in formal languages. English is highly, as I said, highly under-constrained natural language, but we do have plural forms also in formal languages. In the most basic form, in a very simple formal language, the language of regular expressions, we find plurals here in the repeating of the group parenthesized as B. So in that regular expression, this regular expression contains a plural, meaning many or any number of B's in a sentence. And strangely, in a more advanced, more powerful grammar formalism, that of context-free grammars, the possibility to express plurals in such a simple form, which is very much comparable to how natural language would express it, just name many, disappears somehow, because in context-free grammar we need to employ some kind of recursion to express a plural. And the downside of this is that when we parse a sentence with a grammar like this, we get and we detect or accept a plural, many bees, then we get a deeply nested parse tree. And this parse tree is really like the encoding of a list as a recursive list with head and tail that you know from functional programming languages or Prolog. So very early in the history of context-free grammars, and their use in the specification of programming languages, it was discovered that the loss of the plural in the regular expressions was actually a loss. So it was reintroduced in so-called regular right-part grammars. These are grammars that allow regular expressions on the right-hand side of a production rule. And you also know this from extended Backus-Naur form, where the curly braces replace the cleany star. So basically, this is a reintroduction of the simple plural of regular expressions. And when you use this, it basically amounts to a loop. It's quite easy to pass this into the plural into a sequence of bees. There's obviously many more languages in computing, and we take a look at modeling languages next. So the archetypal modeling language of our days is the UML, and UML distinguishes in its structure diagrams, static structure diagrams, between a type and an instance level. So let's have a look at the instance level first with the singular case. I was speaking of my computer on a previous slide. So how would I express this in UML? Well, there's a class person, and I myself am an instance of this class, and then there's a class computer, and these two classes are related by an association or maybe an attribute of person named computer. And the singular case would express that in general, I can have only one computer. So I would find this on the instance level in this diagram. Myself is a person, I is an instance of person, and my is an instance of computer. And then I have this object diagram relating myself to my computer. The plural case on the type level is very similar. The only difference is that I replace the one, expressing the singular, with a star, expressing that there can be any number, including 0. And on the instance level, what I find is just an enumeration of my computers. And so they live side by side in a way like in the regular expressions or the regular right-part grammars. The type level is mostly about the declaration of data structures, and the instance level is their instantiation. So I can have examples, but what do I need these languages for? Basically, one of the most basic things that I can do, I can navigate data structures. So here I have myself as a person, and using a textual language that allows me to navigate these data structures, I would just write I, which is the name of the instance person that represents myself. Now, the person has this attribute, which you saw as a relational association in the previous diagram, called computer, and it links myself to a computer. So to access or navigate this association or relationship or attribute, I just write I.computer. And my computer has a CPU, and the navigation continues by just adding another dot and the name of the attribute of the computer. So that is a very easy expression, which gets me from myself to the CPU of my computer. And the nice thing about these modeling languages is that there's no difference in the navigation expression when I switch to plural. Now I can have many computers. Referring to myself is still the same. and then referring to my computers is just I computers, and then from there on to their CPUs, I just add the attribute name. So syntactically, it is just the same construction. Navigating singulars or plurals is the same. There are, of course, other modeling languages, for instance, the language of relational data modeling. In that case, it's also fairly simple. Everything in relational data modeling is a flat relation, including instances like myself. I would represent this as a relation that consists of a single tuple. The tuple has only one place occupied by myself, and then computers and CPUs are probably binary relations relating person to computers and computers to CPUs. So on this level, there's also a distinction between associations from one to one or from any number to one and to many. And these are sometimes called mapping constraints. Of the constraints to one, we have one to one or n to one. And of the constraints to many, we have one to n or m to n. So the n here is a plural, and the one on the right-hand side is relates to a singular. But again, this is a difference in declaration. The mapping constraints are usually provided with the declaration of the relations. When I want to navigate the relation, the expressions do not differ. Here I navigate from myself via the computer's relation and the CPU relation to the CPUs. And here I take my and your computer and I navigate using the same expression. That's a bit like in natural language, where the difference in the expressions between my computer runs and my computer's run was rather tiny. Guess what's coming? It's not so tiny in programming. So when I look at object-oriented programming here in its graphical depiction, using again UML as a language, in the singular case, I have an attribute called computer, but this time it relates not to precisely one computer, but 0 or 1. This accounts for the nullability of pointers in object-oriented languages. But now, the plural case differs in another respect. It's not a difference in the cardinality, but it's a difference in the type of the attribute. Now I refer to a collection, and the collection refers to any number of computers. So the difference in number has now become a difference in type, which does matter quite a bit, as you will see in the next slide. So when I navigate in object-oriented programming, then again here, for your memory, I computer is a singular of type computer, and I computers is also a singular, but of a different type, collection of computers. When I navigate these expressions, I can write I computer get CPU to get to the CPU from my computer, but in the plural case, I need to employ a construction like this one. And this is rather different. And the reason why it is different is because computers has a different type than computer. And the problem with this is that even though this is a parametric type, which also names the computer, the container dominates the content. And we don't have that in the other languages. It's a peculiarity of programming. So let's look at the mother of all languages, mathematics. Do we have plurals in mathematics? Oh, yes. The first occurrence of plurals is in the solution of equations. Here's a simple equation. And you learn in school, of course, that this equation has two solutions, -2 and 2. But how do you write this down? I have three alternatives. Let's have a look at the first on the left. Well, this looks right at first glance. Two solutions, that would be a set containing -2 and 2, but it's actually not true, because if you substitute the set for x in the above equation, you can't even evaluate it because the square of sets is undefined. So the second seems all right, but it's actually not, because it does not say that the equation has two solutions. It only says that you can get a solution by selecting from -2 and 2. So actually, the correct way of putting this down, at least what I learned in school, is exactly like this, is that there is an and. I have one solution, -2, and another solution, 2. And the reason why I need to put down the indices is because if I use a logical conjunction, which constructs a plural, in mathematical terms, it would be wrong if I used x on both sides, because x cannot be both equal to -2 and to 2. So there's this subscript, x1 and x2. But this is the correct way in mathematics to express that the above equation has two solutions. It's a plural. And similar problem, prime factorization. For instance, 12 is the product of 2, 2, and 3. But the prime factors are a genuine plural. Again, as above, it's not a set. It's not a set in this case in particular because 2 occurs twice. But it's rather something like x or factor 1, factor 2, and factor 3. Okay. And in this case, it's rather different because how many factors you have is also part of the answer. So it's even a little more tricky to put this down correctly, the solution. And another form of plural that we found by looking at mathematics is interval analysis. I'm not sure whether everyone is acquainted with interval analysis. It was actually developed in the context of computing, and the inherent imprecision that's inherent in floating point arithmetic on a computer, which is always imprecise. So with interval analysis, you actually express some kind of non-determinism. So an interval expresses a number, but it does not say exactly which number. It only says that it must be from the interval. And the key point is that other than with sets, you can actually compute with intervals. And you can look at this a bit like a set comprehension. Think of an interval comprehension. So you know that the result of this computation is some number from an interval that is the smallest interval that would result from any number of the first of the two summands. Okay, and in this case, it's an interval described by 2 and 4 as the endpoints, because the smallest numbers would be 1 plus 1, and the largest one would be 2 by 2. And we know, because of the continuity of addition, that this is the monotonicity, that the result must be within there. But you don't actually add intervals. It's just you add very many numbers. You add plurals. So it's not really a container. And one way of finding out that it's not a container is that you cannot nest intervals. You can nest sets. That's a very specific thing, the sets, that you can nest them. But for intervals, this does not make sense. We also have many structures in mathematics that appear to be plurals, but are actually not. For instance, sets, which I just mentioned, but also vectors or matrices, and basically everything that you find in APL. I put this in because people always come with, but APL has it all. Yeah, it has it all, but these are not plurals. Everything, all of these of the above are reifications. They are single mathematical objects that reify a plural. And reification of a plural means turning it into singular. And because it's a singular, you can use all of mathematics that you can use for other singulars to work with them, which is very convenient, but this is not what we're looking at when we look at plurals. Again, all these allow recursive nesting. And this is very powerful because nesting does make a difference. So the empty set is different from the set containing the empty set, and using this infinitely recursive structure, you can build arbitrary structures. And one way to get out of this nesting thing is saying, well, all these are really polymorphic, so it's always a set of something, and you can exclude a set of sets if you like. Yeah, but mathematics is largely untyped, so this is not really an escape, and at least while we're in mathematics. Finally, in mathematics, there's one structure that is very important to computer scientists, actually, which very closely relates to the artificial language that we had in the beginning with irregular expressions and context-free grammars, and this is the string monoid. The string monoid is comprised of a monoid operation, concatenation, an empty string, epsilon, and then the sigma star, which is the Kleene star. So sigma is a set of symbols, and sigma star is the set of all strings of symbols. And they are basically constructed from taking the empty string and the elements of sigma and concatenating them. And then the result is a string, and the concatenation of two strings is also a string. And there's no nesting. You cannot have strings of strings unless you define your alphabet to be an alphabet of strings, which would return to the polymorphic thing. But the string is not the only monoid. We have other monoids in mathematics, and one is, and this is particularly important in this talk, one is the set monoid, in a way, where the strings are replaced by the power sets over an alphabet, and the concatenation is replaced by the union, and the empty string is replaced by the empty set. What you get from this monoid is also flat. You just have flat sets with elements from sigma, and the empty set is among them, and every element of this, the power set of sigma, is also a set, and it's an element of the power set. And again, if I take two sets and join them using the union operator, I get another set of the same kind. This is basically how we construct plurals in language using AND. Okay, and finally we come to something that's central to the paper, the theory of bunches. The theory of bunches is not very well known to most computer scientists. So I'll give you a few examples. All you can see here are bunches. So one is a bunch. It's called an elementary bunch. It's comprised of just one. 1 and 2 is a bunch. It would be a plural in our case. The empty bunch is a bunch. True is a bunch. True and false is a bunch. And ABCD, arbitrary symbols, is also.
Friedrich.
We've lost the audio, Friedrich. If you can hear us, we can't hear you. We can see that you're moving the mouse on the screen, but again, no audio.
Mm-hmm.
The audio is back.
I have, yeah, it was working on my machine. I just checked the settings and it did work. Okay, so where did I lose you? Now it's
At the
muted
beginning
again.
of
Okay.
the current slide, but now it's fine.
Of
You're
the
good to
present
go.
slide. Yeah. Okay.
Mhm.
So in the top row, the first line, you see bunches, and think of bunches as sets without braces. It's just as well that I wrote my sentences down. Okay, so as an immediate consequence, if you relate to bunches, there's no distinction between element and subset. These two terms do not really make sense because there's no nesting. We just have one relation, which is called the sub bunch relation, And basically it says the empty bunch is a sub-bunch of the bunch comprised of just one, and one is a sub-bunch of the bunch one, and one is also a sub-bunch of the bunch 1, 2. It's if you add the curly braces, then it's actually the subset relationship. But since we don't have them, it's sort of slightly different. Yeah, that's a repeat. And I'll skip over that. It's the original author also uses the colon as a typing relation, which sort of justifies the choice of the symbol. So if int is a bunch of all integers, then one colon int means that one is a sub-bunch of integer, but it's also an element of the type. Okay, so bunch theory was introduced by Eric Hainer in the 1980s at the University of Toronto in Canada, and it's not very well known, as I said. I wouldn't really know how many people use it. There is this one article by Morris and Bunkenbock, which is a very formal article, but still great if you want to dive into the details. Generally, it seems like to me like a very small, a very tiny little theory that is extremely widely applicable. It's a bit like fuzzy set theory. Wherever you build something using sets, you can make these sets fuzzy, and you get a fuzzy theory or fuzzy variant of your theory. But also interval analysis and interval arithmetic are sort of related to bunch theory. And that's one of the main reasons why we actually wrote this body of knowledge article, because we wanted to add the knowledge about this this bunch theory and how it serves as plurals in computing to the SLE audience. So bunches are basically plurals. They are always flat. They have this constructor, the comma, which is used as a separator and as an operator. So the bunch comprised of 1 and 2, and I read this comma as and. The bunch comprised of 2 and 3 gives me the bunch of 1, 2, and 3. So this would be bunch union, just like set union, and as the linguistic and constructor that I've been using in English. And it also can be considered a monoid. Again, we have an alphabet, in this case, the integers, and then the comma as a sort of operator, the monoid operator, and the empty bunch as the neutral element. And this actually hints at the denotational semantics that we are going to give for bunches. It will be basically the set monoid without braces. Okay, so no, it will be the set monoid, sorry. So what can I do with bunches? I can actually compute with them just like I can compute with intervals. So I have the bunch of 1 and 2, and I add it to the bunch of 1 and 2. I get as a result, and you can regard this as some kind of distribution. I distribute the bunches over the plus operator, or the elements of the bunch. So I get 4 subadditions, and they evaluate as usual. And so as a result, I get the bunch 2, 3, 4. That's a bit like an interval arithmetic, if you recall, which gave us the interval from 2 to 4. The main difference is here that bunches like sets are extensional. They're actually, well, they're actually enumerated more or less. Hina also does it with infinite sets, non-enumerated. And another example, I multiply the elementary bunch 2 with a bunch comprised of 1 and 2, and I get as a result 2 times 1 and 2 times 2, 2, 4. And this tells you something about a bunch theory. There's a price tag attached to it, because now you can see that one bunch plus the same bunch is not the same as twice the bunch. I just gave you an example. You can also have bunch logic, and it works just like bunch arithmetic. Basically, you distribute the elements of the bunches over the operator. So if I have true and the bunch comprised of false and true, I get true and false, and logical and true, which is false and true. And negation for false and true works the same. And if so false and true, negated is true and false. but of course you can swap these because it's sort of set semantics. But if I do a conjunction between false and true and true and false, it distributes again, and I get as a result true and false or true, which means, unfortunately, that the basic law of Boolean algebra does not hold. The same as above. But that's not a problem because basically what this talk is about is not about bunch arithmetic, which is sort of similar to interval arithmetic, but rather to navigation between objects. And then I don't have these laws, and what you just saw there seems totally irrelevant. It's only if you want to apply bunches to numbers and to logics. So let's have a look at a more general notion than addition and logical connectors. Let's have a look at functions. And functions are basically the predicates of a sentence. They express what is being done. And as you saw previously in one of my initial slides, we can have two forms of predicates. We can have singular and plural, and I will make this distinction here too. So we start with singular semantics of functions. Okay. There's a rule of substitution, like in the lambda calculus. When you apply a function to a bunch, then what happens, you apply the function to each element of the bunch individually. So you substitute each element of the bunch for x in the term, and then you get a bunch of substituted terms, which is the result of the application. For instance, negation, again, if I apply this negation function to false and true, I get true and false. Or in another example from the previous slide, if I apply the function x plus x to 1 and 2, I get 1 and plus 1 and 2 plus 2, which is 2 and 4. And finally, and this is rather interesting, function application is strict in the empty bunch. If I apply any function, any body term here, to the empty bunch, then I get the empty bunch. And this is actually quite neat because in programming, it means that you don't have a null pointer exception. So there's no problem with null, with nothing. It just works like everything else. And basically what you do when you apply a function to a bunch, you distribute or iterate over the arguments. And if I look at this graphically, you can see a function here or an n-to-1 relation. And if I apply it to a bunch, then it maps to a bunch. Okay, and basically this is mapping that you know from functional programming and also all object-oriented programming languages. It's the main difference is that you don't apply it to a container like a list or a set, but you just apply it to a bunch, which is not reified. But that's crucial. That's a crucial difference. Excuse. So bunch functions have one speciality that I don't have in normal bunches, and that is the fact that the body of a function may also be a bunch. So I have a lambda expression here whose body is a conjunction. Did you lose audio again?
No, I just want to remind you that you are running a little bit out of time, 5 minutes more.
Okay, yeah, okay, thank you. Yeah, thanks. Okay, so yeah, I guess I need to rush. Now, if you you apply the function the body is a plural, and if you do that, for instance, x and x plus 1 in the body, you apply this to 1, then you get actually a plural as a result. That is, you map a singular 1 to a plural. Okay. And here's another example of that. I'll skip over this. And basically, this is now no longer a function in the mathematical sense, but it's a relation. But the key message is that application works just the same. Okay, so if I apply this relation to two plural, then I get, in this case, also a plural. Okay, so plural semantics is the variation of this in which I substitute the variable with the whole bunch. In this case, taking the negation, it doesn't really make a difference if I replace X with false and true all at once. So I'm not iterating over it. I get the same result. But when I do it for the X plus X example, I now add the bunch 1, 2 plus the bunch 2 in the body, and I get a different result. Okay, so it does matter. Basically, in the graphical depiction, it means that I'm no longer mapping over function application, but I'm actually mapping many to many directly. So why do we need plural semantics? Why is it interesting? Well, first of all, it allows us to lift the strictness. I can now apply a function to an empty bunch and will not get an empty bunch. For instance, the constant function that returns 1 applied to the empty bunch actually returns 1. And I also need it whenever I want to reflect on a bunch. For instance, I can define equality of two bunches as bunch A being a sub-bunch of bunch B and bunch B being a sub-bunch of bunch A. I could not do this by iterating over the elements. So plural semantics is something that's we need to consider. And I'm going to skip over the denotational semantics because I already said this. Basically, the semantics of bunches is sets being flat, no nesting. Okay, but otherwise you can more or less replace the bunch union with set union, and you just need to remove the curly braces to come back from the sets to the bunches. Okay, so this one is, I'm going to skip over it. This is just a depiction of the relations. Let's have a quick look at the applications of bunch theory, or the plurals in that case. One thing is I can invert functions. So here's a definition of the abs function, which returns the positive of any number. It's implemented using a case analysis. It's pretty straightforward. If I apply this abs function to the bunch comprised of -1 and 1, I get 1, which is it's correct. So both map to 1. But I can also invert this function by using another definition, which also uses a case analysis, as you can see here. And if I apply this inverse of my abs function and apply it to 1, I get -1 and 1. So that's neat. That's something you could not do. You couldn't even express in a typed language because one would be mapped to an integer and the other would map to a collection of integers. Okay, with bunches, this is not a problem. One caveat, forget about it. And the other nice thing you already saw, I have this object structure here, which I want to navigate, and I can use it with bunch functions.
Friedrich,
Also,
can you hear me?
yes, I'm finished. I can hear you.
So did you finish?
Yes.
Okay, let's thank the
Yes.
speaker. So we have time for 1 or 2 quick questions. From the audience? Not? Yeah.
Can you hear me?
Yes, can you hear me as well?
Yeah, I can hear you well.
All right.
I shall leave the floor then to Thijs. Okay.
Sorry?
I can leave the floor to Thijs. I just leave the stage. Okay.
No.
Well, but then
there
we
is one
can't hear you
question.
anymore. I'd like to ask a question, please.
Oh, sorry.
So you've shown us these bunches and how to program with them. Would you suggest that bunches should be integrated into a programming language, or
Absolutely.
should we build a new one on top of it? Because it looks quite different from how we usually consider plurals in programming languages.
Absolutely. I mean, there's a few languages that already do this. OCL as a constrained language does it, and some query languages also have this possibility of navigating over many and one alike. Actually, I defined a programming language called num, which is basically a num for number, which basically distinguishes between singular and plurals. And so this is, in a way, the underlying theory of such a language. Definitely. I mean, that's one thing that we as programmers learn first, is how do we iterate over collections, the old for each statement. And if you have a program in which you use a singular and you want to change it to a plural, it's usually means a lot of work, because you need to look up all the uses of declaration and change them. And if you had a distinction between singular and plural and an implementation as bunches, as I have shown, then it's just a walk in the park.
Okay, thank you, Friedrich, for this interesting talk.